Okay, hey guys, so this problem I think is fairly straightforward. You probably want to use superposition here. Do the problem once with just this, and do the problem once again with just this. So once with just the point load, or once with just the distributor load, once with just the point load. Find the deflection at point C due to just the distributed load. Find the deflection at point C due to this point load, and set them equal to each other. And that's how you get this P here. But the real question I think you guys are probably wondering is how do you deal with this change in EI? Remember that so far I've been drawing my equations like this. What I've been doing is saying that this is equal to 1 on EI times the area of my moment. That's basically how I've been treating this so far. In reality, though, I should be using, that's because the E and I has been constant. If EI is not constant, I should use this equation, this form. So all I need to do is take my moment diagram. Let's say my moment diagram looks something funny, like this. It says 2 EI and 1 EI, right? Well, doesn't that mean that, let's say that this is A, B, C. Let's say that from A, B equals 2 EI and BC equals just EI. And that this is the graph of my moment diagram. Do you guys agree that that's basically the same as just cutting this part in half? So this is now my M on EI diagram. All I did was I brought the EI over here. I looked back at my original problem and I divided it by the coefficient of EI. Sorry, so this should be, so it says 2 EI here. I just divided by 2 here, but really you can just divide it by 3 instead. And that will be, this will be the area that you should use now. So if I want to use my moment area equation again, let's say I want to use x bar. Let's say I want to find the deflection at point C, right? I want to find the deflection at point C. I'm going to take the area of this. Sorry, let's say I want TCA. That requires me to use the entire area here. I'm going to want to take this area, multiply, let's say the centroid is right here. This is x bar 1. So this is A1. That's area 1. This is equal to area 1 times x bar 1 plus this area. Let's say the centroid is here. X bar 2, A2 plus area 2 x bar 2. And that will be the TCA for this problem. So basically go up here, take your moment diagram, in this region of your moment diagram, divide that by 3. In this region of your moment diagram, do nothing, so your moment diagram will not be continuous. Your moment diagram will have a jump in it like I have here. And then use your deflection equation, use your TBA equation. So take the area of each segment. So the area of this segment, multiply it by the centroid from the point you're interested in to the centroid of the shape you're interested in. Area of this shape times this distance. I'm making a big deal about which centroid you take because you do not want to multiply by this one. You always take the centroid about the point that you're interested in. I'm interested in C. The first letter is always the point that I'm interested in. If I'm interested in TCA, TC with respect to A, I need to take the area of the entire shape from C to A times the distance of the centroid from C to the centroid of this shape. Because I have irregular shapes, I broke this up into two parts. With that, so if you do that once with the point load, sorry, with the distributed load, you should get delta at C due to W. This is not, delta at C due to W. If you do it once with the point load, you should get delta at C due to the point load. You're going to set these two equations equal to each other and solve for P. So you have some unknown force here. Let's call this, you have P up here as well, so I don't want to use P twice, but let's call this PB. PB. Solve for PB. And again, it's easiest if you use superposition here. And I think that's everything for that problem. Let us know if you have any questions.